Thank you. I really appreciate the invitation to be here today. It's a great way to kick this off. Excellent first talk, and I'd like to thank the organizers for having me and say it's a beautiful place to be here, and I'm really excited to be talking as part of the KITP. So yeah, I'll be talking about some different effects related to different types of materials, going back to some of the things that Rudy was talking about, and also looking at some different geometries. And really what we're interested in is trying to see if we can find ways in which we can tailor the interaction between macroscopic objects by affecting the vacuum fluctuations that are occurring between them. And so before getting too far into that, I just wanted to give kind of a brief overview of some of the Casimir force experiments that have happened over the last several decades. And I thought, being one of the first talks here, that would be kind of a good introduction. I obviously can't fit everything into this, so my apologies if I've missed some of your favorite experiments, but I'll try to do the best I can here on one slide to give you a condensed version. So starting back with Casimir's original prediction back in 1948, we're all familiar with that, and it took about a decade or so for there to be some experiments about that. So there are two experiments that came out in the first decade, the ones by Deryagan and then by Sparnay. Sparnay did an experiment that was very much in the same spirit of what Casimir was talking about with two parallel plates. However, due to charging effects and things like that, it was hard to make a conclusive statement about how well this matched the theory. And in fact, what his comment was just that it doesn't contradict Casimir's theory. That was, I guess, as close to a confirmation as we can get at that point. But we also have the sphere-plate configuration that Deryagan was working on. And that's the one that is more similar to what most of us work on these days, because the geometry of a sphere and a plate, it has a lot of the same physics that you get from the plate-plate configuration, but experimentally it's much more amicable because you don't have to worry about keeping the plates parallel. So you then have to go forward another kind of 2 decades here until we see some significant improvements in these types of measurements. And so in this case, they were able to take care of the electrostatic interaction better. And so basically by applying a counter bias, we can start to remove some of the electrostatic effects that may have been present in the first couple of experiments. And then it kind of stayed there for a while. And then again, a couple decades later, we kind of come into the modern era of Casimir force measurements. And there were a few experiments here that were really seminal. So there's this experiment here by Lamoureux using a torsional balance and basically modern electronics and modern techniques. We also have the experiment of Mohideen here, again using a more modern way of looking at making force measurements, in this case using an atomic force microscope. And for those of you that are not familiar with the atomic force microscope, the way that works is you can think about it kind of like a record player where you have a stylus that would kind of be in place and you've got the records moving around. Instead, you can have a sample and a sharp tip made typically of silicon. And as that sample or the tip moves around, you can monitor the deflection of that signal via a laser here. And so you can map out topography. And so the reason that that's interesting for thinking about Casimir force measurements is because it's a very sensitive force a sensor here where any sort of up and down motions can be very small, and we can get that amplified via this deflection laser. And so if you replace that sharp tip with some sort of object like a sphere, you can then look at the interaction between the plate and the sphere as these approach. And so that was the way that those types of measurements are made. There's also a branch of modern experiments that are looking at MEMS-based devices. So these are micro electromechanical systems. So these are small mechanical objects that you'll find in airbag deployment or your cell phones and things like that, but they can also be used as very sensitive force sensors as well. And so these are the kinds of methods that were mostly employed, and kind of moving forward, a lot of these types of techniques have been used to make more accurate measurements of the Casimir force. And here's what one of these MEMS devices looks like. And so I'd kind of call this first several decades kind of force measurement advances. Of course, there have been a lot of advances since then as well, but this was kind of really the focus in this regime. And then next we have one way that I like to think about it is other ways you can start to manipulate the Casimir force. So one is looking at the effect of the dielectric response, and the other one is looking at the effect of geometry. And so I'll briefly mention a handful of experiments in both of these cases as well. So looking at geometry, in this paper here, they went back to looking at the plate-plate configuration. So you might notice that in this whole history leading up to this point, there's only one plate-plate experiment here. And so, again, it's really difficult to do it that way, so they were able to, again, apply some modern technologies in order to look at the plate-plate configuration. Then there have been a number of modifications in geometry here, looking at, for example, gratings and looking at lateral effects, looking at nano trenches and other sorts of microscale structures here, looking at using the MEMS devices to make interdigitated nanostructures. So with these MEMS devices, it's again using some silicon-based platform where you can now make kind of on a 2D array, you can make objects that have some sort of structure to them that can then move in and out in one direction, and so you can make these sorts of structures here. And then recently we've been looking at other sorts of systems that are kind of three-dimensional in their extent, and how you can manipulate the Casimir force there. So the idea with this one, for the sphere-sphere system, which I'll talk a little bit more about later, is that we then have these three-dimensional objects, and instead of just scanning in Z, we also have to make sure that we keep our alignment in X and Y, so within the plane as well. So we do raster scanning within the plane and then force measurements in the vertical direction. So then we can talk about the effect of dielectric response. And so here are some of the first experiments. We're looking at dissimilar metals here by Ricardo. And then that was followed up also with some experiments on hydrogen switchable materials. One thing that's kind of interesting with the hydrogen switchable materials is these are materials that, at least over the visible, they may look transparent in one condition, and then when you expose them to a different atmosphere, they change their reflectivity. So at first glance, you might say, well, if it's very reflective, then that looks like the normal sort of Casimir force. If it's more transparent, maybe it's not confining those modes as well, and therefore you might expect a weaker Casimir force. But in this experiment, they actually weren't able to distinguish the difference between these two systems. And so this brings us to start thinking more about some of the complications in what happens with the Casimir force, right? Because it's not just a single frequency or a small band of frequencies of fluctuations that are involved, but it's actually a very broad band system. Right, and so even though over the visible, it looks like we have some strong changes in the reflectivity, that's not necessarily manifest over the entire frequency range. And so that's the reason that they believe that this did not cause a significant change in the Casimir force, because it was basically only affecting a small range of frequencies. There are then some experiments, performed some experiments in fluids, so looking at kind of a three-body system, which is more similar to some of Lifshit's earlier work, where they were looking at kind of two plates and then a medium in between them. And by changing the materials involved, you can find that you can get both attractive and repulsive interactions in that case. Experiments were then done with some semiconductor plates, transparent conductors, so materials that have good metal properties in terms of being able to deal with the electrostatics and the zero frequencies, but are also transparent in the visible. And in that case, you can reduce the Casimir force by about 50%. Then thinking about ways that you can modulate the Casimir force, for example, looking at a phase change material where you can change the dielectric properties by some sort of external process, in this case, example, heating. Looking at graphene in magnetic materials, and then also looking at anisotropic materials, as Rudy was talking about earlier. So this gives kind of a brief overview of some of the experiments that have been going on in the Casimir effect. So today what I'd like to talk about is kind of these three topics here. So first looking at experimental work on different geometries, then anisotropy. I actually won't spend a lot of time on this because we had a lot of discussion of this from the first speaker. And then also talk about some of our recent work looking at what are called epsilon near zero materials. Again, looking at kind of the dielectric response of different types of materials. So first talking about geometry. So this goes back to the kind of AFM type experiment. These are the ones that we do as well. And so this is what the configuration looks like. Here is an SEM of one of these spheres. So you can see we typically, in our experiments, we have a radius of somewhere typically around 50 microns or so. Some of the other experiments, for example, what Umar is working on, and I think Ricardo as well, are generally a little bit larger spheres, and they're able to measure out the larger separations. We typically are in the kind of tens to maybe a couple 100 nanometer separation regimes here based on the size of our spheres. And so I'm not going to go through the entire measurement scheme here. We have more details in this paper or some of the other ones. But basically, we use a combination of different lock-ins so we can apply oscillating voltages between the sphere and the plate. And then we can apply a DC bias as well to try to interact, to remove out any sort of electrostatic interaction. So this is akin to kind of a Kelvin probe force microscopy sort of setup. So you do this in order to remove any sort of electrostatic interactions. We then oscillate the position between these two as well. So we have a piezo here that oscillates this plate separation. And so as you do that, you can look at the interactions of the sphere as well. And so what happens is as you move that plate up and down, the sphere will start to oscillate. And we can break up the different components there into basically an in-phase and a quadrature part. And those will tell us different things about the Casimir force and also a hydrodynamic force. Because the experiments we're doing, they're actually in an air environment. And so we have a hydrodynamic effect as well. If you're working in vacuum, then that is minimal or goes to zero. But actually for us, it's a bit of a benefit. We use that in order to allow us to get closer to contact because it gives us a little bit more kind of squishiness so we don't actually get too close and have it snap to contact. So the air pressure helps us with that a little bit. Anyway, so you can go through all of that, and then you can measure the Casimir force, or actually what we're plotting here is the Casimir force gradient, because that's proportional to the signal that we get. And you can compare that then to Lifshitz expression here, which is in the solid line. You can see there's generally a pretty good agreement. And again, for experiments we do, we're usually from a couple of tens of nanometers out to a few hundred nanometers. And so this, you'll also notice that this is for the sphere plate geometry, the typical sort of one. But more complex geometries are very interesting. And I showed a number of geometries that were looked at in the past. And one thing that really motivated us was this calculation here. Now it's been a while ago, but the thing that was interesting here is that they found that if you have this situation where you have kind of a needle and a hole, as they like to call it, you can actually get a repulsive interaction in vacuum between two metals. And this is one of the very few examples of such a system. And so that has motivated us to look further into different types of geometries. And so here is the sphere-sphere geometry, which I said this is the first one that we looked at in terms of being able to have kind of 3D structures and looking at the Casimir force between them. And the way that this works is we do a typical sort of Casimir force measurement, as I was describing previously. But in between each Casimir force run, what we do is we stop and then we scan. We raster scan this like we were with an AFM. You can just imagine that this is kind of like a very blunt tip AFM. And so we can image one sphere with the other sphere. And so that's what's in the background here, is basically using one sphere to image the other. And so then what we can do is we can determine how much we've drifted away from that center. And so then we can correct for that and then run another force run. And so we do that for about 24 hours so we can collect enough data to get relatively good force data. And here are some of those experiments. And so these are experiments where we've kind of broken this down into three plots here, where we have a total of 9 different spheres and looking at different force runs with each of them. So for example, in A here, we've got this sphere right here, and then we do measurements between this sphere and each of these 3 spheres, and we can plot that all in the same plot here. Similarly for the other ones where we start off, for example, with this sphere, and we measure the force between these 3 and plot that here. And so what you'll notice here by looking at some of the statistics is that in some cases we'll find that the spheres, even though they might look like pretty good spheres, there are some deviations and errors associated with them. For example, we think that this one is slightly not as spherical as we would like it to be, because you'll notice that whenever you have this sphere interacting with any of these 3, there's always a little bit of a dip right here. And so that's evident that it's an effect of this sphere, because if you look at this example here, where we're also using all 3 of these with a different sphere, we don't see that. So you can start to see some of these types of effects as well by looking at multiple measurements from different types of spheres. But anyway, so this is what that looks like, and in general, they tend to agree pretty well with the Lifshitz theory. So what we've been working on the last few years is looking at some of these different geometries. And so here are a few examples. So in the first one here, we're looking at a sphere and a vertical pillar. And so we can change the size of this pillar and look at the force interaction. Here we have a pillar with a hole in the middle. And so we make the pillar here relatively wide so that it's acting basically like a flat plate with a hole in it. So this is thinking a little bit more about kind of that needle and hole sort of situation. But of course, our needle in this case would be huge. It's much bigger than the the hole, so it's not quite there, but just gives you an idea of the way you can modify it. And then we also have looked at periodic structures, where we take kind of a single pillar here, and we make arrays of them and look at the interactions in that case. And so I'll talk about each of these individually a little bit. So in the first case where we have a sphere and a single pillar here, we see as we change the radius of the pillar, so that's right here, if we have a relatively large radius of the pillar, so about 3 microns, then this basically looks like a sphere and a plate situation where the pillar is a plate, because the force interaction is mostly between the top of the pillar and this plate. Now, as we start to reduce the radius, we start to see that there's a reduction in the magnitude of the force, and there's also a slight change in the slope here. And so this is one way in which we can start to engineer this a bit. If we look at the force gradient here of the pillar versus that of, so when I say pillar, I mean the sphere and the pillar versus a sphere and a plate, we can start to see for example, for the large radius, it basically doesn't change much for short separations. It's effectively acts like a big plate. But as we go to smaller ones, we see that there's a reduction, and as we get to larger separations, it starts to increase again. And that's due to effectively the sphere starting to interact with the underlying plate as the radius of the pillar gets smaller and smaller. And you'll notice that there are some dashed lines here. The dashed lines here, these are using Lifshitz expression for the force, along with the PFA approximation. And so we found that for most of our data that this approximation actually works surprisingly well for all the systems we've looked at. However, I'll mention that Benjamin Spring, postdoc in my group now, he's been looking at some exact approaches here. And so he'll talk a little bit about that at the poster session, and you can find out some more details there and so forth. So here's the first situation. The second one, we look at a hole here. And so in this case, you also start to see a pretty strong deviation in the power law here. And actually, one other thing I'll mention, if I go back to this one, I'm talking about, in this case, we start to have a bit of an increase in slope here, meaning that it starts to look a little bit more sensitive to the force. So this would be good if you're thinking about applications where you want to make a sensor that's more sensitive to separation. So that's one reason that you might want to start thinking about going to smaller and smaller pillars. You have a stronger force dependence. Here we're actually weakening the force dependence some, where if we look at, again, this is the whole diameter now. So we're starting off with, again, a pillar that is a 3 micron radius, and then we're putting holes in it. So when there's 0 holes, effectively the pillar that's large, so it looks like a sphere-plate interaction. As we start opening up that hole, we start to see the decrease in that force, but then at larger separations, it starts to more closely mimic what the other ones are. And so you see that here as well. So we start to get more interaction between the plate as well. The outside radius of the ring is 3 microns. 3, yes, correct. And then the final set of experiments we looked at here was for an array here of pillars, and so the pillars here are 300 nanometer radius pillars. And then we change the periodicity here of them as well. So when you've got the single pillar, we have this configuration here where we said there's a fairly large power law, very sensitive to distance discrepancies, or distance, very sensitive to the distance. And as we decrease the radius, or sorry, decrease the period here, we start to increase the force law here. And we can look at how the force is enhanced compared to that of a single pillar as you look at different separations here too. So again, these are some experiments we're now going back and we're looking at some exact calculations in order to see some of the different effects there, and also extrapolate out to larger separations. You'll notice that with these, because the forces are relatively weak here in our configuration, we're limited to about 200 nanometers or so, because we're starting to hit the noise level for our experiments here. So we'd like to also look at what would happen at larger separations, could we measure out there. Okay, so next I want to talk about optical anisotropy a little bit. What happens if they're optically anisotropic? Well, we heard from Rudy that you'll get a torque, right? Because you think about if you have 2 materials here and you've got some sort of confinement of the fluctuations, now that energy associated with that now depends on what the angle is between these different these 2 materials, and therefore there will be an energy dependent or the energy will depend on the angle, so you'll get a torque associated with that as well. And so we also have a review article here that we're talking about a number of different phenomena that have been predicted related to torque. But I just wanted to point out just the more general, less maybe exotic things here. So here are just if you have two birefringent plates. We're actually looking at different birefringent plates here. And what you'll see is that for short separations, there's this 1 over distance squared force law. We also recovered that at large separations. So at short separations, there's this analytical expression from Parsegian and West that says that it should have that sort of behavior, but it also behaves that way at large separations. The reason that we're looking at this with two different materials here is because there's a sign change, which is also discussed in the previous talk. So that's kind of interesting in this case. So there's no liquid crystals here. These are just two birefringent plates with vacuum in between them, but there's still a sign change associated with one of them based on what the optical properties are. And as Francesco was asking about earlier, that is also related to kind of what, depending on the distance range that you are, which frequencies are important. So when you're at close separations, certain frequencies are important. When you go to larger separations, it's a different set of frequencies. And which axis has the largest dielectric function then varies with frequency. And so that's why you get this sign change here. And then we also see that there's a sine 2 theta dependence for the torques with these systems here. And so I'll just spend maybe 2 slides or so talking about the experiments that were mentioned earlier. And so what we were looking at was we wanted to measure this effect. And if I go back to the slide, so you'll see that the torques are relatively small, so kind of sub nanonewton per meter here. And so you need a fairly sensitive way to measure that. And so the liquid crystals are actually a really good way to do that. So if you have a liquid crystal, it's effectively a birefringent material as well. If you have a birefringent disk here, as you bring this liquid crystal close to this birefringent disk, there will be an interaction between these two. And so then what happens is it'll cause the liquid crystal, if it's anchored at one end, to start to rotate to align its optical axis with that of the other birefringent crystal. And so in that way, you can start to get this rotation of the liquid crystal, which you can then optically measure. And so that's what we show here. Again, this is the configuration where you've got a liquid crystal, a birefringent crystal here, and some sort of gap between them. In this picture, it's shown as kind of an air gap. However, this would be very difficult to do as well. So what we end up doing is we actually put a solid isotropic material in here so we can then let the liquid crystal wet the surface and it's still separated from the other birefringent material. And so that's how we're able to do this. Now, for that sort of experiment, you'll then notice that you can't just easily change the distance, right? So you actually have to make new samples for every distance that you want to try. And so that's what we do. Here's the optical setup. So you've got your liquid crystal right here. There's a spacer layer that's isotropic here, and then the birefringent solid crystal here. We shine polarized light through and look at how that gets rotated going through. And here is a photograph of what one of these samples looks like between cross polarizers. And so this is a 1 centimeter by 1 centimeter sample, and it's broken up into 9 different regions here where there's a different thickness of this spacer layer between the liquid crystal and the birefringent crystal in the bottom. And so when there's no spacer layer, you'll see that it's bright, and as you increase the thickness of it, you'll see that it gets darker. And that's because it's related to how much rotation you're able to get through this layer. And so effectively, this is showing us the strength of the torque. When it's a light color, it's showing you that there's a very strong torque. When there's a dark color, there's a very weak torque. And so you can visually start to see that there's a torque. And so this is how we measure the torque for a fixed angle at different separations. So again, you have 9 different samples here. If you want to look at the angular dependence, that's another trick. So what you have to do for this case is you could make a bunch of different samples where you, rather than keeping this angle at 45 degrees, you keep it at some other angle. But the other thing you can do is you can actually, at this top part, rather than having the liquid crystal all lined in one direction, you can have it circularly aligned. And so this is what we call a circular rubbing, because that's the way you make, you rub a surface with a polymer on there so you can get it kind of going in circles so that the liquid crystal will then stick in circles along the top. And so then you look at deviations from the circular behavior at the bottom. And when you look at that through cross polarizers, it looks something like this. And you'll notice that this one looks fairly symmetric. On the next slide, I'll talk a little bit more about this. But by looking at this, we can also determine whether or not there's a torque. There's obviously a lot more to analyze with this, but I'll show you visually. You can look at that too. So here's the experimental data here, along with the theory with the solid lines for a liquid crystal and 4 different birefringent solid crystals as well. And so what you'll notice here is I've kind of grouped them. If you look at these pictures at first glance, these all look basically the same, and they have some sort of fourfold symmetry. However, if we look a little bit closer, we'll notice that it's not quite symmetric. So for example, if I look at this first one, I'll notice that this dark region here is a little bit narrower than it is over here. It's a little bit wider on this side. And so that's saying that it's kind of squeezing this a little bit in this region. And so that's evidence visually that there's a torque happening here. Again, you have to go through the analysis of this data to actually determine quantitatively what it is, but qualitatively we can see that. If I look at the lithium niobate one here, we'll see a similar sort of behavior where it's kind of a little bit narrower here and a little bit wider here. So again, there's a torque. If we look at the next one, the titanium oxide here, we'll notice that in this case, it kind of switches which one is wider. This one now is a little bit wider here, it's a little bit narrower over here. And so that corresponds to a different sign of the torque. And similarly, you'll notice that with this last one here. So the first two here have an orientation that gives you what we'll define as a positive torque, so a torque in one direction, whereas the second two give a torque in the opposite direction. And so you can visually just see that from the data here as well. But anyway, so here's the data. So we see there is the sine to theta dependence, and the sign of it depends on the which materials we use. We can also look at the distance dependence here, which is shown here again, the data points. And then also we have solid lines. And I mentioned for each sample, each of these kind of 1 centimeter by 1 centimeter samples, we can get about 9 different distances out of it. So we actually have a number of different samples here, which are denoted by these different symbols. So we've got circles, upside down triangles, and squares. And so each of those correspond to one sample with 9 different separations on them. And you can see how they kind of line up fairly well with the theory in these two cases. And so moving on, we're now starting to look at some of these other situations where we can start to see, is there a sign change with distance as well? And so we think that that's a really interesting thing to look at. And to comment, I guess, on what Rudy was mentioning with the cholesteric liquid crystals, this I think also would be a very interesting experiment. And it's not something that we have gotten too far into, but I think that I don't see any real reasons that that's a showstopper. It's a matter of taking a look at what the optical signal would be, making sure that the rotations could be detected. But I think that's another very interesting direction to go. And then finally, I want to talk a little bit about some of our recent work looking at epsilon near zero materials. And so whether or not you're familiar with this sort of terminology, basically there's ENZ or NZI materials. So people that are more interested in kind of optical studies and ways of engineering photonics and metasurfaces might be more familiar with these. But ENZ is referring to epsilon near zero. NZI is near zero index, so we're talking about with epsilon the dielectric function, or with the index of refraction, and basically where that goes to zero. And so here is a nice plot here showing for different frequency ranges, so from the ultraviolet through the infrared, where you have different materials that might have, or that do have, some sort of NZI or ENZ-like behavior. And so you might be wondering, well, so, okay, there are some naturally occurring materials that do this. You can also make artificial materials like metasurfaces that can do this. But in terms of naturally occurring materials, it's quite easy to see where you get this sort of behavior. So if you take a simple Drude model, and we can use a material like indium tin oxide, which is actually a pretty good material for ENZ studies. Whenever you have a Drude model, what happens is the dielectric function, the real part of it, it goes through zero at some point. So naturally, you have an ENZ point for any Drude model. And so the question of whether or not that's useful comes down to what the imaginary part is and how lossy it is. And so as long as the loss is relatively low, then it'll also have a near zero index. If the loss is too high, then the index will be relatively high by comparison, and so then you don't necessarily get the NZI behavior, but you'll always have ENZ because it goes through zero. So here's indium tin oxide. Even materials like gold have that behavior. But the thing you'll note here, where that occurs, the ENZ frequency for gold, the plasma frequency is 9 eV, so that's the ENZ frequency. So that's kind of beyond what we usually are working with in optics, right? So that's a too high of a frequency. So that's why people don't usually use gold for these types of effects, and also the loss. So that's what ENZ materials are. And so could they affect quantum materials or quantum systems? And so actually, maybe before I say that, just for optics, this is interesting, right? Because if you start thinking about the dielectric function where it goes to zero, if you look at Maxwell's equations and any of the sorts of solutions or other sorts of systems you look at, epsilon comes into that all over the place, right? And so if you send that to 0, a lot of times you'll get either a 0 coming out or an infinity coming out. And so there's lots of interesting nonlinear effects and things like that that can be explored in kind of the optics realm. So then you could say, well, are there interesting quantum phenomena as well? And so there's a really nice paper here that came out a few years ago where they looked at a cavity made of an E and Z material, theoretically, and they said, well, what happens to quantum fluctuations? And so it turns out for an ideal E and Z material, well, you can have fluctuations of the electromagnetic fields outside. Inside this cavity, there are no fluctuations. And so any phenomena that is dealing with quantum fluctuations, whether it's spontaneous emission or the Casimir effect or anything like that, they're all going to be influenced by this in some way. And so are there implications for Casimir physics? And so some of the first things that we were thinking about was, well, okay, imagine if you had this E and Z cavity and you put some parallel plates in there. Well, as it becomes E and Z, you no longer have fluctuations, so the Casimir force goes away. Now, this would be great if we could do this, but this is where that bandwidth problem comes in, right? So for the Casimir force, it's broadband. And so you would need an E and Z material that would be broadband to all Casimir frequencies. And so that's probably not possible. You could also think about E and Z coatings, where you could maybe put coatings on these materials and suppress fluctuations. But again, you have a bandwidth problem here. And so we looked into a couple different situations where we found that we could see some interesting effects. One is looking at this system where you have a perfect magnetic conductor and a perfect electric conductor, and then put a thin film on top of here. So this is a metallic-like film that has an E and Z frequency associated with it, and looked at some of the properties of the E and Z frequency and the thickness and how you can tune this system. So you can actually make stable and unstable equilibriums in this case. And we also looked at ways in which we could try to control what modes would exist between in some sort of Casimir cavity, so between a sphere and a plate, and then see if we could electrically modulate this. So we could electrically modulate the Casimir force by changing what modes can exist in this cavity. So for the first part, I'll talk about this system first. So you may recall, you know, if a traditional sort of Casimir force that's attractive between two materials that have a pure electric response. There's some nice theory a while back by Boyer and others, where they looked at if you have a magnetic material and electric material, you can get a repulsive interaction. And then there have been some clarifications on these kinds of what kind of criteria you have. This is kind of pure magnetic and pure dielectric here. You get pure repulsive. If you have real materials, then there's some criteria about how good you can get the repulsion. But what we're interested in here was saying, well, what if we put a thin film on here that has some E and Z frequency associated with some thickness? Can we modulate what this repulsive force is? And so here's the result of looking at this sort of system. So in this first set of calculations, we're looking at a thickness here of about 150 nanometers. And what we did is we looked at, as you vary the plasma frequency or the E and Z frequency and the separation, what does the force look like? And so we see there's two different regions here. There's an attractive region and a repulsive region. And so you could kind of imagine this, traditionally, if you take your plasma frequency to be very high, this is then a very good metal. And so you have what's looking like a very good metal interacting with another very good metal, so you get attractive interactions here. If you let the plasma frequency go very low, you'll find that it looks more like the perfect electrical conductor interacting with the perfect magnetic conductor, because this material here starts to become transparent, and so you get your repulsive interaction. Another thing you'll notice here is that depending on both your separation and your plasma frequency, there is a stable equilibrium that's reached here. So at this intersection between the attractive and the repulsive, if you get further away by moving up in this plot, it's attractive, so it'll bring you back down. If you go below, it'll be repulsive, so it'll push you back up. So it's a stable equilibrium here. And then at shorter separations, we have an unstable equilibrium, where when you get closer, it's attractive, and when you get further away, it's repulsive. We can then look at some cross sections here in this contour plot, and that's shown here, where we're looking at the crossover frequency, and again, kind of for large frequencies, we get this where it's always attractive, looking like two parallel plates. For small frequencies, this starts to look like a perfect electric and a perfect magnetic material. And the offsets here, kind of the distance in the vertical scale here, is based on what the effective cavity size is. Because as you have, we have a separation here, and then we also have this distance here. As this becomes transparent, then you get kind of a different distance here associated with that. So these are kind of cavity effects as well. So the other thing we can look at is we can fix the plasma frequency and look at what happens when we change the film thickness. So that's what's shown here. If we focus in on this regime here of thicknesses, so from basically 0 to about 4 microns, what we can find is that depending on, so we fixed the plasma frequency, but we changed the film thickness here, going from about 50 nanometers out to 200 nanometers. We find for very thin films, we're in this regime where it's always repulsive. For the thick films, it's always attractive. And at intermediate separations, we see both of these, the stable and unstable equilibrium points, and the distance between these varies depending on the film thickness as well. So you could think about this also as some sort of force sensor. All right, and then the last thing I wanted to talk about with this was looking at how we could modulate the Casimir force. And so, again, if you have two metal plates that are good metals, we've got strong confinement. If it becomes less good of a metal, so think about it as a low plasma frequency, it becomes more transparent, and so then this would have kind of a weaker Casimir interaction. And so if we could electrically switch between these two configurations, we could electrically control what modes exist in the cavity and also the Casimir force itself. And so one way to do that is looking at these systems that involve indium tin oxide, which is one of these E and Z type materials that I referred to before. And we can put it in kind of a capacitor-like configuration, where we have a metal, a dielectric, and either a semiconductor or another metal. And as you apply voltage, then you can start to get charge accumulation on one of the surfaces. And as you do that, you're changing the charge, the free charge carrier density, and hence you can change what the plasma frequency is. So here's an example of one of these systems where we have basically indium tin oxide, an insulator, and a metal here. And as you change that charge density, you can start to look at how you can change the index of refraction and the real and the imaginary parts of that. So there have been a number of experiments where people have shown that you can do this modulation. For the most part, even when you apply voltage, the charge accumulation is usually in the first few nanometers here. So you're really only locally changing where you have that charge density, instead of locally changing what the index of refraction is. And here's another example with titanium nitride. And so what we were looking at was the system with indium tin oxide, having a thin insulating layer here of aluminum oxide and then gold on the other side, and then applying a bias between these two. So the bias is usually something on the order of say 0 to 5 volts. If you get too large of a bias, then you'll start to have breakdown here, and so you won't be able to sustain your charges you're accumulating here. And so then we used a couple different models looking at what this accumulation layer thickness is, and so we kind of bounded it from 1 nanometer to 5 nanometers thick. So this is kind of the region that we expect to be operating. And you can see going from 0 bias out to a few volts, we can get a couple orders of magnitude change in the charge carrier density. And then the next slide, I'll show you how that affects, well, I guess here, how that affects the dielectric function. So we're looking at the dielectric function now as a function of bias voltage. And so you can see that as you go from 0 to 6 volts, how we can increase that bias. And so now if we have all of this, we can now calculate the effect on the Casimir force because we now know how we're changing the dielectric properties. And so this is the configuration that we're looking at. So we've got a gold sphere, this MOS type capacitor configuration with the voltage. So we apply electrical bias, we modulate the charge density, and so we get a change in the index of refraction. And so by changing that index of refraction, we can change what the 0-point energy is associated with the cavity and modulate the Casimir force. And so these are calculations that we've done so far looking at this. And so at a separation of 10 nanometers, we can see that we can actually get hundreds of piconewtons of force with biases going up to maybe 5 volts or so. We can look at this difference here. For experimental regimes, we're generally going to be looking at kind of more 30 to 40 nanometers. And you can still get several piconewtons of force variation there. So this is an experiment we're currently working on. Sorry, I don't have any data to show you for this right now, but hopefully next time we can talk about that too. So with that, I'll go ahead and wrap up here, saying that we wanted to look at controlling and engineering the interactions with the vacuum and materials. And we showed that you can do this. There's lots of interesting forces and torques, and there's also lots of new things to continue to do. So with acknowledgements and recaps, we looked at effective geometry, the effect of anisotropic materials, and also E and Z materials. And with that, I'd like to thank my group, some of our collaborators, and our funding for that as well. So thank you.
Okay. Thank you, Jeremy, for this talk. We have a few minutes. Okay. I think it's... No?
Hello? Nope. Still not?
That's better, yeah. Excellent talk, Jeremy. Really wonderful. Getting back to your phase change materials, one of the really interesting questions going back many years is what happens if you have a superconductor? Either one side of the cavity is made superconducting, or you insert a superconductor into a regular Casimir cavity. What are your thoughts on the possibility of that, and the possibility that the Casimir effect will alter the properties of the superconductor, for instance, the critical field or the transition temperature? Just general thoughts.
Yeah, great question. Yeah, I think that's a really interesting concept to be thinking about. For the types of experiments that we're doing, I think it's not very experimentally feasible because of the temperature changes we need. One of the real difficulties in doing a Casimir force measurement, if you're using an AFM type system, is that the AFM cantilever itself, it's a very good thermometer, if you will, right? But if you change the temperature a little bit, the cantilever will start to bend, which will mimic a force. And so for the experiments we do, we're actually working at room temperature, and we actually elevate the temperature a little bit, a few degrees, so we can keep it all kind of thermally stable at that one temperature. Going to significantly cooler environments is difficult for what we're doing. I know that some other groups, I think, in fact, Umar, I believe you've been working with that, right, down at Liquid Nitrogen. So maybe he can comment on that as well. But it's usually just keeping the temperatures the same between your tip and your surface are a bit difficult. We've been thinking about this problem a little bit in terms of, could we do something more of an optical experiment as well to try to look at what's happening in some sort of cavity that's kind of a fixed cavity, kind of like we did with the liquid crystals. And I don't have too much to say about that at this point, other than I think it's an interesting direction, and that I think it probably would have some sort of effect on the critical field, but I don't have anything quantitatively to say about that.
Okay, Umar, and after Mauro.
Hi, Jeremy.
Hey.
Excellent experiments. Can you comment on, when you do the experiments with the geometry, like how well we can subtract out any electrostatic effects because of this, side edges and such?
Yeah.
And it's being done in air, so is there a limit where you can do? You can only do at short distances, you can do it any limits that you run into? Yeah.
Sure. Limits based on electrostatics, or?
I mean, yeah, like how, when the electrostatic effects will kind of mess up the experiment.
Yeah, that's a good question. And so, I mean, we're mostly limited right now in terms of just our force sensitivity, right? Because the way that we're doing it, we can measure fairly well at close separations, but at larger separations, it gets significantly harder. And it's more of a force sensitivity than an electrostatic, issue in terms of getting more electrostatic force, because obviously that dominates when you get to larger separations. But I think one of the things that's also hard to say is, I mean, so you've got your kind of traditional electrostatic calibration and cancellation you do by oscillating voltages and whatnot. There's also, variations in the surface contact potential difference, right? And so for the sphere plate or plate configurations, you can kind of understand more what's happening on your surfaces, because you can do good Kelvin probe force microscopy and things like that. For these structured ones, I think it's a little bit more difficult because you've got all these different surfaces and you can't actually probe all of the different areas. And so we're looking into, doing the Kelvin probe force microscopy over the entire system. And I think that that's probably a pretty good way of determining what the electrostatic forces are. But we can't really probe, in between the pillars and things like that very well, or the edges very well. I think that we're mostly covering that, though, by, kind of going on the outskirts of it, and if there's any sort of stray field, it's going to be detected by your cantilever as well. But it's definitely more of a challenge, I think, in these other geometries.
Yes, hi, very nice talk. So just a question about this epsilon near zero business. So you say that at some frequency that there are no fluctuation inside this cavity. But how this is compatible with the black body, which does not depend on epsilon? It's universal, so
I guess I'm not sure. Maybe we could talk more about this later. So if you're talking about black body, there's not a maybe I'm not quite following the question, because if you heat up any sort of object, like a real object, then it has an epsilon associated with it. But a black body, by definition, I guess, of epsilon, it's kind of it's always absorbative, right? So you've got just the imaginary part is infinity, I guess. Or?
No, if you have a very big cavity with walls which are not which are corrugated, so you can avoid multiple reflection. Okay. In the center of this room, the walls are the same temperature, you're supposed to have blackboard in the middle.
Okay, on the inside of the cavity is
Yes,
black.
but you
Okay.
said there are no fluctuations. So how is possible there are no fluctuations? You have blackboard.
Heisenberg principle.
So.
I don't know. I'll have to get back to you on that. So I can refer you to the paper. So this work from.
Yes, I know.
Yes. Okay. So I'm not sure. I'd love to talk more about it this week. Yeah.
Okay, we thank Jeremy again, and we have a break, 20 minutes more or less. We start at 11 o'clock.